All right, so this is the second hour of Physics 1C for March 31st, and we're solving this problem right here. It's a 10 mega ohm resistor connected in series with a 1 microfarad capacitor and a battery with an EMF of 12 volts. We can write down all that information right over here. We can say we've got a resistance R that's equal to 10 mega ohms. 10 mega ohms is 10 times 10 to the 6 ohms. And then we've got a capacitor with a capacitance that's equal to 1 microfarad, so that's 1 times 10 to the negative 6 farads. And it's connected to a battery with an EMF of 12 volts. So we're going to assume that's like the ideal EMF and that it has no internal resistance. Before the switch is closed at time t equal to 0, the capacitor is uncharged. So we've got a system where we've got a capacitor with a capacitance C, a resistor with a resistance R. Those are the symbols we use for those guys. It's connected to an EMF source like this. So this is going to be our EMF source. And then there's a switch somewhere in the system. The switch is thrown at t equal to 0, at which point the capacitor starts to charge off. And we want to solve for some things. The first question is, what is the time constant? The time constant is this thing that we call tau, right? So it's equal to R times C. So this is pretty simple, right? It's just 10 times 10 to the 6th multiplied by 1 times 10 to the 6th, negative 6 farads. And we saw that this gives you units of seconds, and this should be 10 seconds, right? All right, then it says, what fraction of the final charge QF is on the capacitor at t equal to 46 seconds? So here's where we need to use our equation. Our equation was that Q of t is equal to the maximum charge, which the maximum charge in the system, Q, is going to be equal to C times E, which is going to be equal to, you can see it up here, basically, 1 times 10 to the negative 6 times 12 means this is going to be 12 times 10 to the negative 6 coulombs. That's our maximum charge. So it's going to be, basically, Q of t is going to be that charge Q times 1 minus e to the negative t divided by R times C. Now, since we've already calculated what this is, we can actually make this quite simple here. Our charge, right? Oh, what are they asking us, though? What fraction of the final charge, right? We need a fraction here, right? So the question is, at Q of 46 seconds, that's the time that they want us to use, right? T equal to 46. What fraction of the maximum charge do we have, okay? And if we plug the things in here, this is e to the negative t, which is going to be 46 seconds, divided by R times C, which we already saw was equal to 10. And this is going to allow us to find the charge on the capacitor. We could find the value if we want to. But if we just want a fraction, we can just divide by this. And that should give us the answer. And this is going to be 1 minus e to the negative, 4.6. Because 46 over 10 is 4.6, right? So what's that equal to? You guys calculate that for me? Really just what this ratio is right here. What do you guys get? Okay, that's part B. Part C, what fraction of the initial current, I naught, is still flowing in the circuit at t equal to 46 seconds? So this is where we need to use our current equation. Our current equation is that I, as a function of time, is equal to the maximum current multiplied by e to the negative t over RC. So this will lead to I at 46 seconds divided by I max should be equal to e to the negative, and again, it's going to be t, which is 46 over RC, so it's going to be just 4.6, right? I mean, what do you think it's going to be? If this is 1 minus e to the negative 4.6 is 0.99, then this should be something like 0.01, right? 1%, right? So this would be 99%, and this would be 1%. I think that's what you're going to get, right? Yeah, 0.01, so 1%. I'm going to add a part D onto this because quite often the example problems from Young and Friedman are just a little too simple. To show you something that's also going to show up on problems like this, we could say something like this. We could say find the time when the capacitor is at 75% the maximum charge. If this is something that gets asked for you in a problem, what you can do is say, I want to find the time, Q of t, that the ratio of the charge at that moment in time divided by the maximum charge is equal to 0.75, which in this case is going to be equal to 1 minus e to the negative t over 10. The 10 again because RC was equal to 10. And then you would just solve for t, right? Which is going to be something like 1 minus 0.75 is equal to e to the negative t over 10. We're trying to solve for time now, so we have to take the natural log of both sides. So we'll get the natural log of 1 minus 0.75, that's 0.25. If I take the natural log of the left side, it just becomes negative t divided by 10 seconds. And then we can solve for t by saying that t is equal to the natural log of 0.25 divided by, I'm getting close to the edge of the screen so it's hard to write here, divided by negative 10. Right? Multiply, oh no, not divided by. It's multiplied by 10, sorry. So it's going to be 10. And there's a negative sign. So it's negative 10 multiplied by the natural log of 0.25. And that gives you the time. So I got like 13.9 seconds. This would be the time when the capacitor is at 75% of the maximum charge. A little bit more than 10 seconds, because 10 seconds represents the time that it's going to take to get to 63%. Okay, that's an example of a problem you can solve with this stuff. Do you guys have any questions? I'll go back up and show you. So part C was, what fraction of the initial current I naught is still flowing at t equal to 46 seconds? So we were calculating when the current is 46 seconds, at 46 seconds, what the value of the current is. We just wanted to find the ratio of that to the total current. Is that clear? You guys have any other questions? These problems are a little tricky, but they shouldn't cause a lot of problems for you, I don't think. You get a few of these kind of problems on your homework. Okay, so we've gotten through step 1 of what I wanted to talk about today, which is RC circuits. We've done this already. So the next topic is going to be magnetism. We're mostly going to be talking about magnetism for the rest of today. We have like an hour and a half left. So let's start talking about magnets. Okay. Yeah, sure. Within a circuit like this? Yeah, so you're saying like if you had a circuit where like you had like a resistor here and maybe another resistor like right here, and then these could be connected to like a capacitor and then another capacitor, for example, and maybe even these are connected to a third capacitor like this, right? And you've got some like C1, C2, C3, oops, some R1 and some R2, And then all of these could then be connected to a battery, right? This is definitely stuff you'll see on your homework, by the way. Oh, I forgot that it does that. So if I put in a battery right here, like here and here, and then I just select a different eraser, small eraser. So if you have a system like this, then yeah, you could reduce these two down. That's my mouse. You could reduce R1 and R2 down, right? To one resistor, and you can reduce these down to one capacitor. And you can imagine multiple kind of combinations of things like this that will show up in your homework problems where, yeah, you could be using series and parallel reduction to simplify the circuit. And then once you've simplified the circuit, you can use that to figure out what the R is and what the C is. And then you could figure out the time constant, right? Is that kind of what you're thinking? Yep. All those rules will still work. We can still reduce all three of these capacitors down to one by adding the inverses of these and then summing the ones that are in parallel. Adding the inverses of these gives you the resistor, all that kind of stuff. So you'll definitely see homework problems like that. Cool. Good question. Okay. Next topic is magnets and magnetism. Yeah, we're on like chapter, I want to say 28 in your textbook now. 27. 27 is the chapter we're on. And there's only, we go up to 30, pretty much to 31. We'll do 32, but we don't do much with it. So we have about 5 chapters left, right? 27, 28, 29, 30, 31. There's about 5 chapters left in this semester. So not much, actually, if you think about it. The topics are pretty dense, though. Like, this chapter alone has just a ton of stuff in it, as indicated by the topics that I listed up here at the very beginning, right? We're going through magnetism, magnetic forces, magnetic flux, circular motion, magnetic field, and these are all applications of magnetism. So, yeah. Okay, so you guys probably know something about magnets, right? Like, it's very easy to find magnets in your home. You've probably got several attached to your refrigerator, right? But that maybe is the extent of what you know about a magnet. I don't know. Maybe you played with a magnet. Maybe you had a toy or something that had magnets inside of it. But we can start off with some basics here. I guess the first thing to say is historically, magnets were first found. According to your book, and I don't know if I can believe this because I don't believe almost anything that they write in these books. They say that magnets were first discovered about 2,500 years ago on an island near ancient Greece called Magnesia. So there's the name. Magnet from the island was called Magnesia. And what they found was there were certain kinds of rocks that would attract little bits of iron. And they didn't really know what was going on, but they gave it a name. They said, here's this thing. It's a rock that can attract iron. And those types of rocks were called lodestones. Okay? I don't know what this name means. I used to at some point. But a lodestone was basically what you might call a natural magnet, a naturally occurring magnet. And these were discovered in like 2,500 years ago in Greece. The thing is, though, if you do any amount of research online about this stuff, you'll find out that everything in our textbook comes from the West, right? It comes from the history of the West. It comes from the Greeks, the Renaissance, etc., right? But it doesn't mean that people in China and in Africa and in South America didn't also know about magnets. They did. Like, people in South America understood what magnets were. They thought that these rocks they found had, like, supernatural properties, and they would use them to find sources of water. Something similar happened in China as well. And I'm sure the Greeks did this too. But the point is that you got to be careful about these textbooks. They'll say something, and it's like, certainly other civilizations found magnets too, right? The difference is that the civilization of ancient Greece, we have so much documents from them, right? We have so much information from them. The writings of Plato, Aristotle, all the, you know what I mean? Herodotus, the histories, all these things. We have all these things that were maintained, and as a result, like, what the textbook tells you is like what we have from them. But don't think that people in other civilizations couldn't figure out magnets too, also, because everyone's smart all over the world, not just in ancient Greece, even though textbooks would have you believe that the ancient Greeks are the only people that ever learned anything. Regardless, so naturally occurring magnet, I went on kind of a tangent there. I really don't like textbooks. So naturally occurring magnets is what a lodestone was. And basically they just noticed that this could attract little tiny bits of iron. That's all they really knew about it. Now eventually, people started to get clever, and they started to do things like say, like, well, suppose that I take one of these guys, right, and let's say that I suspend it in midair, right? So I take a little magnet and I spin it in midair, and I'm gonna kind of use the modern notation of what we use for these things, which is that we say that one end of the magnet we call a north pole, and the other end of the magnet we call a south pole. Okay, they started suspending these things, and it took the Greeks a lot longer to figure this out than the Chinese, but the Chinese figured out that this magnet would point in a certain direction. And this is a phenomenon that you guys all know, which is that this thing can be used to produce what's called a compass, right? This is one of the first major uses of magnets. The way that the Greeks did this, I believe, is they would have like a bowl, and they would have the magnet float on side of water inside the bowl, and then the direction the magnet would point. They figured out pretty quickly that this type of a magnet, it always makes it so that the north end always kind of points toward the north pole of the Earth. So I don't think they really understood what was going on. They just knew it worked, right? These things basically always tend to point north. And if you have an ability when you're out in the ocean to know what direction something's pointing, that's very valuable. You can also use things like astronomy to figure out what direction north is, right? You just have to find the North Star. But this gives you even more accuracy, right? As you tilt your boat, you know exactly what degrees you are away from north, right? Without having to use the stars. So it's a very powerful device that could tell you where the north direction is on Earth. But the thing is that magnets are much more powerful than this. They can do so much more than just tell you directions. But this is the introduction of how we learned about magnets, right? Often in history, we learn about things, and then we find much, much later on, the applications of them go well beyond what we've been using them for. And that's what happened in the 1850s with people like Faraday and Maxwell, as they discovered the connection between these magnets and electricity, which we'll discuss today. So that's the basic thing, though, right? It's a compass. The north end points to the Earth's North Pole. And the reason for this is because the Earth has its own type of magnetic field. And I've got a couple pictures of that over here for you guys. What the magnetic field of Earth kind of looks like. So there's this one from your textbook, and then the other one over here is from a different website. So I'll give you two little pictures of this. Maybe before I even do this, I should say something else about magnets, which is that, no, I'm just going to go ahead and show you this real quick. So this is like what the Earth's magnetic field or magnetic poles look like. Okay, two different pictures. One on the right is a lot more detailed. The one on the left is from a textbook, so it's obviously kind of simplified a little bit. But this is what we call the magnetic field of the Earth looks like. Okay, it has these circular kind of nature to it, and it basically the Earth's magnetic field is such that the north pole of the Earth is actually, here's what it says right here, the Earth's magnetic field has a shape similar to that produced by a simple bar magnet, although actually it's caused by electric whatever. The Earth's magnetic axis is, where does it say it? Here it is. The geographic, this right here, the geographic North Pole is actually the South Pole of the Earth because it attracts the North Pole of a compass, right? One of the things you can say about magnets is that if I take a magnet here and I orient it such that this is the north side and this is the south side, and I put another magnet right here and I orient them exactly in the same way so that this is the north side and this is the south side, you guys probably know there's going to be repulsive force in this direction on each of the magnets, right? And like the same pole basically attracts or is repelled by the same pole. If I put the south pole of a magnet like right here, and I put the south pole of a magnet right here, then there's also going to be a force that repels them just like this. But if I place them so that we have opposite ends, so if this is the north end and this is the south end of the magnet, right, then there's going to be attractive force between these guys, right? So repulsive on these two, and on these guys, there's going to be an attractive force between the two of them, right? Now, the effect of this is if I take an object that is able to spin on its axis, okay, this part might not be so obvious, and I place it into a magnetic field, okay, and a magnetic field has lines just like an electric field like this, okay? When I put an object that is capable of detecting the magnetism, like a magnet, and I place it into a magnetic field line, what will happen is that a thing that can oscillate will line up with the field line. You see how these little compass needles here are lining up with the direction of the field lines? And in general, just to kind of say a little bit more about this, if I take a magnet, like a bar magnet, so this is the north end and this is the south end, then I can draw magnetic field lines, and they look something like this. They always go away from north and towards south. So the magnetic field lines end up looking something like this. They have this kind of circular nature to them. Like this. On the bottom, they tend to kind of go around like this. Not going to do a great job of this, but this is kind of in general the idea. These are kind of what the field lines look like for a bar magnet, and that's basically what's being shown right here in 3 dimensions. Okay, we would call these the magnetic field lines. And something you may have seen before is if I go to here and I look for iron filings, you can see a picture of what these things look like. Here's an example right here. Here's an example right here. Here's an example right here. This is an even better example right here. Pull this up. Oh, this is a video. Do you see all these little lines right here? How they're curvy? There's these little like points that come out of here, but you can see a pattern, right? You can visibly see that those little lines, they represent the magnetic field of this here. And if we were in classroom, I would show this to you. I would take a magnet and iron filings, and we'd do exactly this. You could see how over time these little iron filings, and probably what's happening here is they're shaking this surface so that the filings can move a little bit. But can you guys all see these nice, beautiful lines that are showing up right here? This is the south end, this is the north end. The lines don't have direction, but every one of the little iron filings is lining up parallel to the magnetic field, right? The magnetic field down here points this way. You can really see a nice line forming right there over time, right? As more iron filings fill in to fill in the gaps. But those are magnetic field lines. That's what they look like. You can visibly actually see them. With electric field lines, we have to draw and imagine these things. With magnetic field lines, we can literally see exactly what they look like. And, you know, it's 3-dimensional. That's why these things are spiking up like this. But there you go. Those are magnetic field lines. You can get magnetic field lines for different orientations. Does this really cost $200? That's crazy. So, anyway. Those are magnetic field lines. And I'm going to erase my terrible drawing here because it just looks bad. But that's what they look like. And then when you exaggerate that for the Earth, they kind of look like this. And then this is a more detailed picture of what they actually look like. Clearly much more complicated. Near the surface of the Earth, due to deposits of iron and all kinds of various things in the Earth itself, you get these very strange looking magnetic field lines right here. It's very complicated. So don't trust what you see in a textbook. The Earth's magnetic field is quite complex. But nonetheless, on the whole, it does act like effectively like a bar magnet. Okay, do you guys have any questions so far about what magnets are? No? Okay, so one question that we want to answer in this course is, what actually makes a magnet act the way that it does? Okay? It produces a force. What is that force? And where does the magnetism come from? Okay? So I'm going to tell you right now, and it's going to take a few weeks to actually develop and prove this to you guys. I'm going to say this, that electric fields, so I'm going to talk about electric fields, but I'm going to tie it back to my electric fields are produced by stationary electric charges. Right, we've seen this before. You take a positive charge, right? It has an electric field. It goes out like this, it goes like this, it goes like this. That's our electric field, right? Magnetic fields Okay, and we use this symbol for magnetic fields. Okay, so this means magnetic. We use the symbol B. It's a vector. So magnetic fields, just a little bit, are produced by moving charges. It's just that simple. And I'm going to prove this to you guys. It's, like I said, it's going to take a few weeks, but electric fields are produced by stationary electric charges. Magnetic fields are produced by moving electric charges. Okay? So, how on earth is this thing a magnet, right? This is what we want to figure out in the rest of the semester. How is it that this object, a magnet, can be described by moving electric charges? And the simple answer is that inside of here, there are electrons. And those electrons are spinning. And the fact that they're moving and rotating produces this magnetic field. And if you get enough of those electrons to all align so they're spinning in the same direction, you get a permanent magnet. That's what a permanent magnet is. And we can design devices that can produce these things. And we use charges to do it. We use currents to do it, basically. Okay. Electric fields are produced by stationary charges. Magnetic fields are produced by moving charges. You guys have any questions so far?
So a bar magnet would be a permanent magnet?
Yeah, effectively, yes. However, not to, yeah, but this is a permanent magnet, yes. The types of magnets you have in your refrigerator would also be permanent magnets, right? These type of magnets, they can lose their magnetization, though. Any magnet that you have, if you heat it up to a high enough temperature, the random thermal fluctuations that the magnet will be subjected to will cause it to lose its magnetism. Does that make sense? Magnetism. Go ahead.
Sorry, can you explain that a little bit?
Sure. I'm kind of jumping ahead a little bit here, but I don't think there's a problem with this because this is an overview anyway, and we'll get into more of the details later. So let me just... Here, let me draw a bigger picture. So what is a bar magnet? North end, south end. Within our bar magnet, okay, there are little electrons, okay? So imagine an electron. Let's pretend for a moment that the electron is shaped like a ball, although I sincerely doubt that they actually are shaped like this. And let's say that this electron, you guys, I think you learn about this in your chemistry course. You guys know that electrons spin, right? Have you guys heard that expression before? That electrons actually spin on their axis? You guys know about that?
I thought they just like spin around the nucleus. I didn't know that they spin around their own axis.
Okay. Well, is anybody else familiar with what I'm talking about? That the electron actually has this property that we call spin?
Yeah.
You've heard of it before, right?
Yeah.
Okay.
Up or down.
Up or down, exactly, right? Okay, now let me work off something that you guys understand a little bit better, actually, because this works just as well. So imagine individually that this object is made of iron, okay? So let's say that our magnet here is an iron magnet, right? Okay. Iron happens to be a really good thing to do with this because it has these strong coupling between neighbors and stuff like that. So let's say that we've got our iron atom here, okay? So here's our iron atom. And while we know that this atom has all kinds of electrons spinning around it, let's focus just on kind of the outermost electrons and say that there's electrons that are going around this object like this. Right? There's little tiny electrons that are spinning around these atoms, right? The fact that the electron is moving in a circle like this, okay, means that it produces a type of current, right? It's a charge that moves in space, right? So in a way, what you can do is say that if the electron's moving that direction, there's a current that flows back like this, right? Does that make sense to you guys? Because the electron's negative, current is the flow of positive charge. There's effectively like a little tiny loop of current right here, right? Does that make sense to you guys? And I'm also going to tell you that if you have a little current loop like this, that this thing is effectively a bar magnet. Okay? This object is 100% equivalent to a bar magnet. This is like a bar magnet that's oriented like this. This is the north end, and this is the south end. And again, we will prove this, but these two things are 100% identical when it comes to their magnetic fields. The flow of the current right here, okay, moving electric charges, is what produces magnetism, okay? So that this is an individual iron atom, and we're looking at just one electron flowing around like that way, it produces a current in the opposite direction, which produces a magnet that looks like this, basically, right? So now imagine that this object over here is full of all kinds of little iron atoms, right? Now, of course, the number of iron atoms you're going to have in here is absolutely extraordinary, so I'm not going to draw every single one of them, but I'll draw a few dots to represent what's going on. And now let's say that we simplify what we mean by a magnet here and say that what we mean by this is really just a vector that points this way, okay? Right? You should be able to see that from this picture up here, that the lines point kind of like through the Earth and out this way, and all the arrows are going in on this side, right? So you can effectively say that this object is basically just represented by a little arrow that points like that, okay? So we say an arrow, right? Because that makes it a little easier for me to show you what's going on here. Now imagine that these things they're all randomly oriented, but that most of them are effectively pointing in the same direction, okay? Not all of them. Maybe some of them are pointing backwards. That can happen for sure. Maybe some of them are pointing this way and some are pointing this way. If on average, more than 50% of the atoms within the system line up like this, then the effect is you end up adding up these. Basically, every one of these represents kind of like a vector for your magnetic field. Every single one of these. And you guys know that you can sum vectors, right? And the sum of all these vectors is going to produce a magnetic field that looks something like that. Does that make sense? So you start with a current, and if all of these atoms line up just perfectly, right? So that they're all lined up with this arrow kind of pointing roughly in the same direction. Not all of them, but if something like 50 to 60% of them are doing so, then you produce this magnetic field. So every atom is like a magnet. You get enough magnets added together, you get a big magnet. That's pretty much what I mean. Does that make some kind of sense to you guys? Did I lose you?
Sorry, the stream was being kind of laggy, but you said like that.
I can go.
That what vectors inside of the magnet representing?
Okay, the stream went laggy a second. I'll just start over again and go through it again because I know from time to time that my stream can drop. You guys can hear me okay now, though?
I can hear you perfectly fine. The video is the problem.
Oh, really?
I just disconnected and reconnected from the stream. And I got better.
All right, should I just stop the stream and restart it for people?
I'm not sure if I was the only one experiencing
Is it working okay for you, for everybody now?
it's working well for me.
I think I got better.
The nature of my internet is that it's kind of like the weather. It kind of, sometimes it's raining really hard, and then most of the time it's just a nice sunny day. I am, however, upgrading my internet to business internet because I found out for some people that might be the only answer to my problems. And then talking to the tech today, it made it really clear that they treat business customers better than they treat residential customers. And that actually kind of pissed me off. But regardless, I think by next week, I'm hoping that I have a more stable internet connection and we don't get those kind of things happening. So let me go back through in general what the idea is. Iron bar, composed of iron pieces that are randomly oriented. If we can get enough of these iron atoms to line up in the same direction, what I mean by that is that effectively, if you have an electron moving around the iron atom, we can treat that as kind of like a magnet. Okay, the current flow produces a magnet. And we think of that idea that this little guy basically is equivalent to a magnet pointing like this. And then we say it has a magnetic field vector that points like this. And then we say, okay, every single piece of our iron atom, if each one of these things all happen to be oriented effectively on average in the same direction, the net effect, if we sum up all of these vectors, is you get a magnetic field that points from left to right. That's kind of the general idea. Does that all make sense to you guys? Now, let's add in the part that I said earlier. Take a, quote, permanent magnet, right? Like one of your magnets on your refrigerator in your wall, or on your refrigerator. And let's say you want to remove the magnetism for whatever reason, okay? What you can do is you can take that magnet and put it in a pot of boiling water and heat it up to just a stupidly high temperature. I don't know if it would work with the magnets on your refrigerator. You might have to get even hotter to make it work. But given enough temperature, right, you're going to induce thermal fluctuations into the system right here, right? You know, you heat this object up, and these things all start to wiggle around, right? It no longer stays in the same place. Let me use a different color. Each one of these is going to start to wiggle back and forth, right? The direction of the atom. And if you add enough heat into the system, enough temperature, basically increase the temperature, these will all start to oscillate randomly, and you can basically destroy the magnetism. Does that make sense? You can use temperature, thermal fluctuations, to disrupt the order in the system. And if you disrupt the order, you can break the magnetism. And you can take what was originally a magnet and turn it into just another piece of iron. Does that make sense to you guys? It would depends on what you do. It probably would permanently remove it. Yep. It would probably permanently remove it. Yep.
Is there a way to fix it?
Sure. And this is something you probably saw if you did any like what do you want to call it? Went to any science fairs as a kid. I'm sure that you saw something like this. You take a nail, right? Yeah, no, this is fine, I guess. You take a nail. No. This is gonna look awful if I try to draw like that. Make it a little more. So I take a nail. So I've got my nail. And I wrap the nail in a piece of wire. So they take a piece of wire that goes around like this, and then back around like this. That should connect. You wrap a wire around the nail. And then you connect this to a power source. So that you produce a current flowing in your system here. And then you guys know that this will make a magnet out of this thing, right? This is something you guys have seen before. We call this an electromagnet. Any of you guys do that when you were kids? Or you can magnetize anything you want to, really, as long as it has what we call ferromagnetic properties by doing this. So things like nickel, cobalt, iron, and some other metals. Things like aluminum won't work, but a lot of certain substances will do this, and it produces what's called an electromagnet that can basically be switched on and off by turning the switch on or off. And you can even change the polarity of the magnet. In this case, the magnet would be, let's see, this would be the South Pole. This would end up being the North Pole with the way it's connected, I think. Right? Yeah. If you switch the polarity of this, you'd switch the polarity of the magnet. Okay? It's really that simple. That's all there is to it. That's basically how you produce a magnet. Take a battery, connect it to a nail, wrap it around like this. This thing will pick up little pieces of paper clips and stuff like that. Okay. So that's how you would restore the magnetism. That was the question, right? How do you restore the magnetism? That's how you would do it. Alrighty, does this all make sense to you guys? So magnetism, right? So let's now that we've introduced the idea of what magnetism is, I want to tell you some features about magnetism that are relatively important. The first one that I think is just extremely important is what happens when you cut a magnet in half. So if I take a magnet, right, and I say this is the north end, and I say this is the south end of the magnet, okay, and then I take this magnet and I cut it in half, then what happens is that you produce two magnets. This ends up being south, north, and this ends up being north-south. We can repeat the process here and here. And again, what we'll find is that we get a magnet here that ends up being south on this side and north on this side. A magnet here that ends up being south-north. Another magnet here that ends up being also south-north, and this one will be south-north as well. So that still the side that was north is north, and the side that's south is south, but every piece that you cut out produces 2 new magnets, okay? Now, one thing that people have kind of thought and wondered since they first started understanding these things is it possible to actually isolate one of the poles, okay? So is it possible to keep doing this cutting process and isolate one of the poles? We'll say a single north pole. Or south pole. Like, can you cut this down enough to where you get just a north pole or just a south pole, right? And the answer is no. You always get a dipole. You always end up with a north and a south. Always, 100% of the time. It is impossible to isolate either a north pole or a south pole, okay? Now, why would we want to do that? Well, there's a lot of reasons why you might want to do it, but the first reason would be, suppose we want to compare electricity and magnetism, right? In electricity, we have single charges, right? An electron has just a negative charge, right? A proton has just a positive charge. You can have individual sources of electric fields, okay? But with magnetism, you always get a dipole, all right? So there's basically no such thing as magnetic charge. And another way that that's said, there's no such thing as magnetic charge. And another way that's said is there are no magnetic monopoles. There's no magnetic monopoles. We have been searching for magnetic when I say magnetic monopole, does that phrase make sense to you guys? It would be something like a single north around which we could draw field lines like this or something like this. That doesn't exist, okay? Or a single south pole around which we could draw field lines. We can't create, for example, a current of magnetism. We can create a current of charges, right? That's what electric current is. It's the flow of individual charges through a system from one portion of the system to the other. We can make that happen because you have all these free electrons that are free charges, and then you can use them to do work for you, right? You cannot create a magnetic current. There's electric current, but there is no magnetic current. Does that make sense? There's no such thing as magnetic monopoles, as far as we know. People have been searching for these for hundreds of years. It is a major and active area of research still today in America, across the world, I should say, at higher institutions. Some of the projects that I worked on when I was in college were about magnetic monopoles. One of the flaws of our modern attempts to connect electricity, magnetism, to connect electricity, magnetism, and gravity, one of the current flaws to our attempts to do that is that a lot of the theories that we produce of the universe, where we try to unify all the forces, one of the things that pops out of these theories is that there should be magnetic monopoles. Does that make any sense? So if we try to, so I'll put it this way. I'll try to write down what I said, because I know it can be really hard to follow these ideas. So there's this thing, we call them GUTs, okay? A GUT is what we call a grand, it's 4:04, we should really take a break in a second. Unified theory. A grand unified theory is a theory that basically unifies the forces of electromagnetism and gravity. This is the goal of modern theoretical physics, is to merge these two into one idea, to bring them together. The problem is certain versions of these guts, we call them just guts for short, grand unified theories, certain versions of these, some of them, not all of them, some of these theories lead to magnetic monopoles. some of them lead to magnetic monopoles. So if we could ever find one of these things, if we could ever prove that one of them exists, it might verify some of these theories. But as it is, the lack of evidence for monopoles makes it very difficult to make one of these things work. You know what I mean? I'm getting very far into like theoretical physics, but I'm sure some of you are interested in this. I'm sure others think this is a waste of time, but it's interesting to me. That's why I'm sharing it with you. Hopefully that's somewhat interesting to you too. But the reality is we've never actually found one of these things. Every time we find a magnet, it comes in pairs, and the fact that we haven't found one is like a proof that these things don't work currently until we can come up with a better way of doing it. And that's what I'm trying to say. But the fact that there are no magnetic monopoles is very important, and we'll talk more about that later. Okay, do you guys have any questions?
So in chemistry, you can have like a solution of ions, right? Like positive and negative ions.
Sure. Yep.
So if we were to like put magnets on both sides and separate the solutions, would it like still not be possible to make a monopole in a way? Does that make sense?
Sure. So the first half of your question. Go ahead. Keep going.
No, it's just like if we literally just like separated the solution like theoretically down the middle.
Yeah.
When the ions were separated to both sides
Mm-hmm.
of a magnet. I
So,
guess is my question.
so first of all, the question would be, can you use a magnet to separate those ions? That'd be the first question, right? And what I would say is that unless the ions are all moving, which I guess they would be, it might be difficult to use a magnet alone to separate them.
Okay, that makes sense.
But you could certainly use an electric field to do that. If you applied an electric field to your solution, you could cause the positive ions to pile up on one side and the negative ions to pile up on the other side for sure. Right? I mean, I can kind of draw a diagram of that, I guess. Like if I've got a solution here, and I've got some positive charges and negative charges in here, just kind of floating around, ions, right? If we apply an electric field to the system, so if we apply an electric field that goes like this, then our system is going to be, so if this is electric field, then our system is going to look something like this. It should cause most of the positive charges to pile up on this side, and most of the negative charges to pile up on this side. Is that kind of what you're thinking about? Is that kind of what you had in mind?
Yeah.
So this, to connect this back to monopoles, this does allow us to separate the electric charges, and there are monoelectric charges. You can have a single charge. Each of these ions represents an object that has an excess charge, right? But these in and of themselves wouldn't be magnetic monopoles. They would just be electric charges. And I would even go so far as to say is every one of these little ions right here, right? Like let's say it's like NaCl or something like that. I don't know, kind of boring, but the sodium ion, which is I think positive, right? This guy by itself is an atom, right? So if this is the nucleus of the sodium atom, then it's surrounded by electrical charges, right? And those charges are going to be moving around in circles. And the motion of those charges means that every one of these ions is basically a magnetic dipole. This is ultimately the problem, is that individual atoms act like dipoles, okay? They act like magnetic dipoles. Even neutrons and protons act like dipoles because they're composed of electrical charges. And electrons, even though they only have one negative charge on them, also produce dipoles. So do you see the problem? The most fundamental things that we know about in nature, the smallest things that we can envision, every single one of them acts like a dipole. Does that make sense? Because every one of them is rotating in some way, and that motion of rotation of the charge associated with what's going on inside the atom produces a dipole, produces a magnetic dipole, and that's the problem. is that at the core, no matter what particle we talk about, it has what's called a dipole moment, which is another way of saying it acts like a magnet. Does that help to answer your question? Basically, each ion is basically a magnet. And not just a monopole, but a dipole. We really need to take a break. It's now 4:10. We'll start again at 4:20. I will close the stream real quick and stop streaming at least.